So we yeah. So go. Sorry for the technical glitch. Yeah, sorry for the technical glitch. I hope now the video will be visible. Mm, yeah. So what is computer network? So computer networks in brief is the interconnection of computers in a fashion that can facilitate the communication between various devices. So what is the purpose of communication? To transfer data. So we need to transfer data from one computer to another and to another computer. And when we have a vast number of computers that are connected to each other, then that is called an internet. So in this internet, a wave of information is getting transferred. So here we have, yeah. So we have one computer here. Yeah. So we have one computer here, and say there is another computer sitting somewhere else in a very far away location. So if they were nearby, they could have been directly connected using a cord. So when we have one computer like this, and then we have another computer which is also nearby, then we can connect that to this one. Yes. So when we have three computers very nearby, first of all, then we can connect like this. Say we have another computer, then we can connect like this. So this is what you call, and then we can connect like this, and this is what you call a star network. Like that, say there is a central server. Say there is a central server here, and now there is one computer connected to this. Usually there is like a switchboard or a server like that in an office. So there are multiple computers which are working on this, the central server, which are connected to this central server like this. So this is the server, this is PC1, this is PC2, and this is the server. So this is a, what is this? This is a hub network. And then there is a final type, which is, there is a central cord line. This cord line is called a bus, and we directly connect computers to this bus. This is known as the bus topology or bus network. So here PC1, so so I think someone has joined. Uh, did someone join? No. Okay. So as I was saying, this is the bus network. So there is a bus network. Yeah. So this is a bus network, and then we have a hub network, and we have a star network. These are the various network topologies. So like if you are connecting in a star network like shown here, this is a star network and this is a hub network. So if you are connecting in a star network, how many links will be there? There will be NC2 links. Okay, and when you are connecting in hub network, how many links will be there? N links. If there are n computers or n nodes, then there will be n links. So if you are connecting from one computer to another computer, this is the like point-to-point communication model. So first, whatever you say or whatever you give as input, that is converted to electrical signals, and then they are modulated, and then they're sent across the channel, and finally they're demodulated, and then again converted back to whatever energy form that you have sent. If it's audio, it will be played back as an audio. If it's a video, it will be played back as a video. So this transducer converts all kinds of media format into bit formats, so that then they can be modulated into analog signals and sent across the channel. So like that, if there are, now what happens if there are even higher levels of networking, like your computers end users are connected to one server, like that there is another office where the end users are connected to another server, but these end users want to communicate with these end users. There is no direct line. And then there is another, say, home network. This is one office network. There is a switch, and all the computers are added to this switch, connected to this switch.
Sir, this is
Yes.
mesh topology or star topology?
Which one?
This diagram, sir, whether is it star or mesh?
This one is actually a hybrid model. Like this one is a hub technology, hub topology, this part, and then these hubs are connected in another hub. So like that.
Okay.
Huh. So so this hub will need another hub to these hubs will need another hub of hubs, like a switch kind of thing, to to communicate with each other. So this device will go to this server, and then this server will go to the switch, and then the switch will decide, okay, so this destination address lies within this server, so I will direct it to this server and not this server. So this switching, what it does is basically it switches one it turns on a particular switch that will connect server 1 to server, like say this is server 1, this is server 2, this is server 3. So 1 2 3, like this, counterclockwise. Okay, so if this is server 1, then server 1 wants to send someone in server 3. Now server 1 will, like one user of server 1 sends the data, it comes to server 1, then server 1 will by using this trunk line. This is the trunk line. Trunk line connects switches and hubs. They do not connect end users. Okay, this trunk line will then connect to a trunk switch. Now at this trunk switch, a decision will be made that since the destination lies in the hub number 3, so we need to forward this packet to hub number 3 and not to hub number 2. And this is the task of the switch. Now this switching will be the main topic of today. So we will learn about various methods of switching. Now can you see data communication and networking?
Yes, sir. Yes, sir.
Okay. So here. So we will go on to the main topic of today, that is switching. So let me just go to the page. Ha. So today's main topic will be switching. Mm, yeah. So here you can see another switch network, another example of a switch network. So previously what I have shown are small networks. Now in this figure 8.1, this is a more complicated network. So here you will see from A to J, there are some end users. A to J are end users. Now these A to J, they are connected to their individual hubs. But all users are not connected to one hub. These hubs are then again connected in a mesh, or in they are all interconnected together. Okay, so all the hubs are interconnected together, but all the users are not interconnected together. Means there is no direct link between A and B, or there is no direct link between A and E, but all the switches are connected together. So what happens is that if A wants to connect to F, A wants to communicate something to F. Now what will he do? A will send its data to switch 1. Now its final destination is F. Now which switch does it need to turn on? It can turn on 2 or it can turn on 5. There are two options. One can turn on 2 or 5 because they are the adjacent switches. So 1, then what happens is that 1 turns on 5. So from 1 the data goes to 5, and from 5 again it sees that the data is for F. So it has many options. It can send to 2, it can send to 3, it can send to 4. But what it will see that the final destination is F. So again it will send to 4, and from 4 it will see that F is within the, like, it is connected to 4. So 4 will just directly, switch number 4 will directly give it to F. So 1, 5, 4, this is the path. Or it can take 1, 2, 3, 4. Like that also it can reach from A to F. Now if it wants to reach from A to I, it will go to A to 1, 1 to 5, 5 to I, like that. So these switches need to be turned on sequentially so that the packet can find its way to the end user. Okay. So now this begs the question. This begs the question, how does the switches know which switch to turn on next and where to go? So there have been, this is the main topic of switching, that which switches to turn on and which to not, because all cannot be turned on at once. You have to make a decision, because if the data is at 1, it cannot simultaneously go to 4, 2 and 5, right? It has to make a decision, and from 5 it again has to make a decision to go to 4 so that it can finally reach F. Now there are three methods of switching: circuit switching, packet switching, and message switching. So circuit switching is the first type, and it is done at the physical layer. So circuit switching is done at the physical layer of the network, and at the data link layer we can do packet switching, and at the application layer we can do message switching. So we will go one by one, from circuit, then packet, then message. So we will mostly be covering circuit and packet. Message switching is something to be taught later because it's more intricate. So circuit switching network simply uses to it takes a circuit switch network is made of a set of switches connected by physical link, in which each link is divided into n channels. So the links are the in like what are links? Links are basically this these connections: 1 to 5, 1 to 2, 2 to 3, 3 to 4. These are called links. So within these links there will be multiple channels. And what are channels? Channel is made by division of resource. Say you have 10 megahertz of bandwidth in a channel. So what you will do, instead of sending one signal over the whole 10 megahertz, which it doesn't need, probably it needs 2 megahertz bandwidth only. So what you do is you send 5 messages at a time. one like using the 10. So a circuit switch network is made of a set of switches connected to by physical links in which each link is divided into n channel. So one way of dividing that, like I said, is by dividing the bandwidth. So that is called FDM, or frequency division multiplexing, FDM. Now another is that you have 10 seconds of time. So what you do is, yeah, so you have 10 seconds of time. Now you don't need 10 seconds after the entire 10 seconds of time to send the whole message. What you can do is you can be done with the first message in 2 seconds. The next message you send for another 2 seconds. Like that, you divide the time into slots. So there is one link. See, between switch 1 and switch 2 there is one link, but there are n channels. Like that, because the thing is, these switches, or why do we need multiple channels in these switches? Because this switch 1 is connected to 2, it is connected to 5. Now if you look at 2, it is connected to 3, it is connected to 1, it is connected to 5. So it requires, like, say A is sending to H, A is also sending to I, and then B is sending to H and G. Like that, there are multiple requests going on together. So if you take only one request at a time, what will happen is, say A wants to send both to I and to G. Now A wants to send something to both I and G, but when it sends something to I, this 1 to 5 channel gets blocked. So it cannot route the G packet through this line. But if it has multiplexing, if it has multiplexing, then it can send both of the data together from 1 to 5, and then another one of the data will go from 5 to I, another data will go to from 5 to 4, from where it will go to G. So 1 to 5, this link can support both datas for A and I, A to I and A to G together, because of multiplexing. And this multiplexing can either be done in time domain or frequency domain. So this one link, this is what is meant by one link and n channels. Now, what will happen is, whenever a particular user in circuit switching wants to send something to another user sitting somewhere else, each, like in each link, one channel is getting assigned for that particular pair A to M. So from if in this diagram, as you can see, from 1 to 4 there is a link. In that link there are n channels. One of that channel will be one, or if necessary more than one. If like the data is large and you need to assign more, then you can assign more than one channels. So one channel in this link will be assigned, and one channel in this link will be assigned. So say you are doing frequency division multiplexing. So 2 megahertz of bandwidth will be assigned here, 2 megahertz of bandwidth will be assigned here also. So like that, you get a clear path from A to M via 1, 4 and 3. So from 1 to 4 it will go, and since the links are created and the channels are assigned for this particular pair, the channel gets assigned. So what happens is, it goes straight away, because it has 2 megahertz of bandwidth reserved here, 2 megahertz of bandwidth reserved here. It will go straight away from A to M via 1, 4 and 3. So first the road is cleared for this packet, and then it is transmitted instantaneously. So there are 3 phases in circuit switching. One is called the setup phase, one is called the data transfer phase, and another is called the tear down phase. So before starting communication, see the flow. Before starting communication, the stations must make a reservation for the resources to be used during the communication. These resources, such as channel bandwidth and time slot in TDM, channel bandwidth in FDM and time slot in TDM, switch buffer, switch processing time, these are all dedicated. So this entire resource of channel, switch, everything is dedicated for a particular pair to communicate. And this is the setup phase. And once the particular pair has gotten all the resources particular transmitter receiver pair has gotten all the resources and has a clear path, then there will be, after a dedicated path is made of connected circuits or channels. So after the dedicated path is made of connected circuits, so once the dedicated path is made, then the data transfer can start. And once the data transfer has started, then it will happen instantaneously pretty much, because all the channels are already reserved, and then we have to tear down the connection, means we have to clear those channels will no longer be assigned to this pair, and it will be assigned to another pair then. So this is, once all the message has been transferred from A to M, then it will be open, that channel will again be open to request for another pair of transmitter and receiver. So is this understood? Is circuit switching understood? Anyone having any questions? Okay. So can anyone tell me what will be the disadvantage of using this kind of a mechanism? Reserving resources for transmitting. What can be the disadvantage? Anyone? Anyone wants to chime in? See, the thing is this, when you are doing this kind of a circuit switching, this is like, you have seen like roads getting blocked when VIPs, politicians, MPs, they go, right? The roads get blocked and you are stuck in a traffic jam, and then the VIP will go, then the entire road will be cleared, the VIP will go, and then again your road will be open and you will be stuck 1 hour in jam because a particular VIP is passing through. So this circuit switching is like that. Circuit switching treats every message as a particular dedicated VIP convoy. So it will clear all the path along the from the transmitter to the receiver. And if at that particular time other users also want to transmit, they will get other channels. But after some point, the channels will expire. There will be no longer any channels left. Then, because all the channels are getting reserved, if more users want to send message, they have to wait a long time before all the users that have gotten a particular reservation right now, they will have to finish their transmission. Then once they finish their transmission, then only he can get his turn to transmit. So this is not very efficient if a lot of users are together trying to transmit, because you have to reserve resources for everyone. So you have to reserve resources. So to alleviate this problem, this is the setup phase and the data transfer phase and the tear down phase, as I said. So in other words, this circuit switching network are not efficient because resources are getting allocated beforehand, and these resources are not available for other connections. Achha. So to alleviate this problem, we will go on to packet switching. But before we go on to packet switching, we will see what is the delay involved. So although circuit switching network normally has low efficiency, the delay in this type of network is minimal. What does that mean? That means that if you do not get a reservation, you have to wait. That is true. But if and when you get a reservation, once you get the reservation of channels for your transmission, it will be lightning fast, because the data is not getting delayed at each switch. Have you ever seen a VIP car going slowly, slowly, slowly? No, they go very fast because the whole road is cleared for them. Who will they stop for? Whereas we, the common people, we will go slowly, slowly because we get stuck in traffic jams. Okay. So that's why this delay for network switching is pretty less, because circuit switching is pretty less. So first we have the setup phase where all the channels are getting allocated. So this is the connect time. This is one part of the delay, and then there will be the data transfer, whatever time is needed for the data transfer, and then they have to disconnect all the channels, means you have to free up all the channels, and that will take another time. So whatever is needed to make reservations in channel that time, plus whatever is needed to tear down the reservations or de-reserve them that time, plus the data transfer time. This will together constitute the total delay in a circuit switching network. So once we are clear of that, we can move on to the next topic of today, that is packet switching. So like I said, circuit switching is not efficient. So you don't transmit all the data at once, you transmit them in packets. You transmit them in packets. So this in data, so what happens is this network, say A, wants to transmit something to X. So earlier, this whole frame used to get transmitted directly to X by making reservations like it will go from this to follow the cursor to this, to this, to this. Or it can go from this to this, then this, follow the cursor. Okay. So there are multiple paths where whichever path is free, you can transmit. That is the circuit switching network. But now we are coming to a new kind of switching network where the data is first divided into small but uniform packets. So each, no matter like if you have whatever data you transmit, say each packet will be of 10 KB. So if you have 1000 KB to transmit, you will have 100 packets. If you have only 100 KB to transmit, then you will have 10 packets. But all packets will be of 10 KB. So if you have more data, you will have more packets, but each packet size will be same, irrespective of whatever the total size is. So data is getting divided into small chunks. These are called packets. Now these packets need to get transmitted to X. So what happens is first the packet 1, it is packet 1's turn. So packet 1 will come. It goes through this switch and then through this switch, then through this switch, and finally to X, and 1 arrives. Then there is 2. 2 will go through this switch and then this switch, and then it will come. Then there is 3. It will go through here and then come. And then 4 will go diagonally to here. But there are other packets also coming to this switch. There is no exclusive reservation. So all the packets are getting serviced first come first serve. So in this particular link, probably channel number 1 got a reservation first. So it went and it arrived first. But packet number 2 and 3 were stuck in traffic. They got stuck in some switch. So packet number 4 perhaps didn't get stuck. So packet number 4 came before packet number 1. Even though packet number 4 was later, because packet number 2 and 3 got stuck in jam, packet number 4 came earlier. Then came packet number 3, then came packet number 2. So there is no guarantee that your data will arrive in order. You have to maintain the order and you have to finally again do a jigsaw puzzle and get back the data in your own order. So you are not guaranteed to get packets like 1, 2, 3, 4. Whichever packet gets least congestion will come. And if some packet gets stuck in traffic jam, then it will come later. Because there is no priority, there is no reservation. Where did you go? Okay. So there is no so this is how the packets will come. This is so irritating. Try to come on time, okay? It's already 6:30. So this is a connectionless network. So this is called a packet network or a connectionless network. Why is it connectionless? Because there is no dedicated connection being made from A to X. Like I am not saying the packet will go from A to X like this. No, the packet might go like this, another packet might go like this. So all packets can take their own routes. There is no direct connection between A to X. Whichever route is empty, they will take that route. So this is called a connectionless network. So there is no setup phase, there is no tear down phase. There is only data transfer phase. From start, you only transmit data. But then why does delay occur? Well, delay occurs because all the packets do not get the particular link. Some may get stuck in a queue. So there will be a particular queue for servicing, and some packets might get stuck in that queue. Now, there is no connection between A and X. So how do the packets know where to go? The packet 3 is coming to this switch here, and then it is going to this switch, and from here it is going here, not here, not here. It is going direct down. So how does packet 3 know it has to first go right, then down to reach X? Because there is no connection. Every packet is going on its own. There is no dedicated connection between A and X. So how does it know? That is where the particular concept of port forwarding or routing table comes. So in routing table, whatever packet is there, all packets have one thing in common. They have a particular header. In front, the packets do not directly start from data. There is a header before the data in the packet. So each packet has a header, and in that header there are multiple informations. So you will learn that as you go through this course. You will learn what all are contained in a data link header, what all are contained in a network layer header. That will come later. But all headers have one particularly common feature. That is, all headers have a particular destination address. All headers know where to go. Finally, it does not know which switches to take because there is no connection being made. But it knows where it has to reach finally. It has the destination address. So whenever it reaches at a particular switch, the switch will check the destination address. And within that switch, there will be a routing table. And say this switch has a particular output ports. Okay, 1, 2, 3, 4. So according to the destination address, for each destination address, there will be a particular output port. For each destination address, there will be a particular output port. So when it sees this switch, sees the data address X for address X computer, this switch sees the address for computer X. What it will do is, it will, 1 minute, let me turn on the pencil. So this, this particular switch here, this switch will have routing addresses. So when packet 3 comes here, it will see, acha, the address is X. So what will it do? It will transmit, it will output from this particular port, So it will output from this particular port, and the data will get automatically transferred here. Now, here there is another routing table. And when it sees the address of X, what it will do is, it will transmit through this output port. Not this one, not this one, not this one, only this one, because it knows ultimately this has to go here. So for each, these switches have multiple output ports, and all the addresses are mapped to output ports. So each address has a assigned output port. So one output port may have many addresses assigned, but all addresses have a unique output port. So address number 1232 cannot exit from 1 or exit from 3. It has to exit from 1. There might be another address that will also exit from output port 1. So this is a many to one function. Okay, this is a many to one function. Now, since this is a many to one function, many to one, so there might be ports which will transmit the address, but each time, but how does this know which address, which port to output from? Well, that is dynamically changed. So each time the data gets transmitted, finally it will see the shortest path and it will update the routing table. So it will update the routing table dynamically. So this is a dynamic table. So this is not something that is coded into the switch or router. It is something that is getting updated continuously. So these routing tables are getting updated continuously based on whatever it is learning. So it is learning the shortest path to a particular address pair, and based on that it will have the output port. Now if you connect the network, if you change the network, it will automatically adjust the output port. So it will be based on the destination address. Now this is of course better because it will ultimately give no reservation. So so it is wanting to be, so this datagram network, this kind of circuit, packet switching is called a datagram network. So this is a datagram network with 4 switches, and this particular datagram network is very efficient because whoever has to send packet can send packet. They do not have to wait for any kind of reservation. So what will be the, so where will the delay come from? The delay will come from queuing. So the thing is, if you are a VIP, like you are in circuit switching, you will never face any kind of delay. But the thing is, when you are doing this kind of a packet switching, here everyone is treated equally. And what happens when everyone is treated equally? Lines. So what happens is, here also there is a concept of queuing. So if multiple, say there are like 3-4 packets coming, which all, according to the routing table of this particular switch, all need to be outputted from this particular port. If all switches there, all the addresses need to get outputted from this particular port, that cannot happen simultaneously. So first the packets have to wait one by one to enter the switch. Then the packets have to wait one by one to exit the switch. So they have to wait, and then again at the next packet they have to wait. So see, here the transmission is going on, but once the transmission is done, it is waiting, and here the transmission is again starting. So from packet A to switch 1 and packet switch 1 to switch 2, the transmissions are not immediately one after another. There is a waiting time involved, and the total delay is the sum of these waiting times and the transmission times. So the total delay is the sum of these transmission times and this W1, W2 waiting times. And then there is another concept. This is also a packet switching network, but this is a hybrid between, this is not purely packet switching like datagram network. The previous one we learned packet, that is a purely circuit switching. And this one is a bit different. This is called a virtual circuit network. This is kind of a cross or a hybrid between a circuit switch network and a datagram network. So here, as in the circuit switch network, there are setup and tear down phases in addition to the data transfer phase. Resources can be allocated during the setup phase, and as in datagram network, data are packetized and each packet carries an address in the header. So this is all like datagram network. So the data is packetized like datagram network, but there is also a dedicated channel. So what happens is, previously what you were doing is, you were in circuit switching network, you were transmitting the whole of data when you are getting a reserved slot. But in virtual circuit network, you are not doing that. You are dividing your data into packets, and each packet, when they are getting a slot, they are getting transmitted immediately. So you have to make packets and you have to wait for each packet to get transmitted. But once the packet leaves the switch, leaves the end user, it will not wait here. So it will not wait at each and every switch. It will wait to start getting transmitted. But once it starts getting transmitted, it will reach immediately. So what happens is, like you have 1 MB of data to send. So you get a dedicated channel. In circuit switching, what you will do, 1 MP means 1000 KB. So in circuit switching, what you will do, you get a dedicated channel. Now you will send 1000 KB like that. Okay. But others will be waiting and you will be sending. Others will be waiting, you will be sending. But in this virtual circuit approach, you will get a slot but you cannot send your entire 1000 KB. You have to wait. You have to wait because you can only send 10 KB. Once you have sent a particular 10 KB packet, you have to wait for your turn again. When your turn comes again, after all have transmitted their packets, you will send another 10 KB. So like that 10 KB, 10 KB, 10 KB, 10 KB you are sending. Like that you have to wait for 100 turns to come send your data completely. So you are not blocking others. But each of these 10 KB packets, they are not getting blocked in the switches. They are getting transmitted immediately. Okay. So now that we have explained the basics of switching and all, now we can move on to the problems that we have at hand. So is there any doubt, any particular doubt from circuit switching, packet switching, TDM, FDM, any doubt? Okay, nobody has any doubt. So we will be moving on to the problems. So the first question is state true or false. In time division multiplexing, all data sources share same frequency. True or false? Tell me. Is it true or is it false? In time division multiplexing, all data sources, means all the packets, share same frequency. Hello, anyone, please respond. Come on, man. Just do a coin toss and say.
True.
Yes, the correct answer is true. Because they are getting divided in time. So, once you are getting divided in time, means like there are 10 packets. The first packet says, okay, buddy, I will take 2 seconds. After that, you come. So he gets 2 seconds. And then for that particular 2 seconds, he has all the resources at hand. The entire network is his for this particular 2 seconds. So he gets transmitted using the entire bandwidth. So he gets all the frequency, same frequency, the entire bandwidth. The next, after 2 seconds expire, the next guy comes. He says to the next in queue that, okay, buddy, I will take 2 seconds. For 2 seconds, the entire resource is his. So again, he goes after that like that. So one after another, one after another. Time division multiplexing is very intuitive. This is how we also do, right? So if we are like at the mess, we are taking food. So what like someone will take again after that guy finishes taking, then another guy will take food like that. This is natural queuing. So our TDM divides time into slots, and each data source is allocated a specific time slot, allowing multiple sources to share the same frequency. So they can share the entire bandwidth. Next, the number of point links required to fully connect 6 customers. So here I have some explanation to do. So the number of point links to fully connect 6 customers. One minute. So the number, there are 6 customers. Customers here means 6 computer or 6 mobile phone, any 6 devices that can connect to internet. So what do you mean by fully connecting? So let's make fully connecting means each device should have the ability to talk with another device. 6 devices. So each devices will be connected to another device. So how many will be there? This is 12 maths. Come on. How many links will be there?
12.
Hi, how come 12? See, each pair should have a link. So these this. What is this equivalent to? This is equivalent to choosing two computers at a time out
Okay,
of
sir.
6. So this is 6C2.
Okay,
So
sir.
at a time you are choosing two computers, you are creating a link. Again choosing two computers, you are creating a link. How many ways can you choose two items out of 6? 6C2. So what is
15,
6C2?
15.
What?
15, sir.
So 6C2 is 15. 6 into 5 by 2, so 15. 15. So it is 15.
Okay, sir.
So this will be option A, 15. Yeah, this will be option A, 15. So next question is, let there be a fully connected network with 8 customers. The proportion of link in use when all customers are busy talking to someone. So there are 8 customers. So they are fully connected, means each customer has a dedicated link to another customer. So each computer has a dedicated link to another computer. So there are 8 computers. So how many links will be there? We have just now read there will be 8 C2 links. So I can solve here only. Wait, where is the things? So total number of links is 8C2 because all networks, all devices are connected to each other. Now what they're saying is the proportion of link when all customers are busy talking to someone. So A is talking to B and then C is talking to D. So like that. So if A is talking to B, so if A is talking to B, how many links are required? One. Between A and B, that link is required for A and B to talk. Like
2.
that, if C and D is talking, then another link. Like that, E and F, G and H. So 8 customers are 2, 2, 2, 2. So A and B are talking, C and D are talking, E and F are talking, G and H are talking. So 4 pairs are there. So 4 pairs means how many links in use? 4. Because there are 4 pairs. One person can talk to another person only. He cannot talk to two persons, right? So number of links in use is 4, just 4. So what is the proportion? Proportion of links? Proportion of links in use is 4 by 8C2.
Sabi into the 11th.
So 4 by 8 into 7 and the 2 will come on top. So this will be 1 by 7. So the correct answer is 1 by 7. Is it understood?
Yes.
Okay. So moving on to the next question. There are 28 links. When all 8 customers are busy, each customer is talking to some other and hence only 4 links will be used. So 4 by 28. Next, suppose we use a switch to connect 11 customers instead of direct point-to-point links. How many switching paths or lines should be available to ensure that no call is blocked? Now this is a bit complicated. See, there are 11 customers who are connected. They are not connected to each other. This is no longer a point-to-point topology. This is no longer a star mesh topology. So this is no longer a mesh So how many switching paths are there? So there are 11 links. Now how many switching paths or lines should be available to ensure that no call is blocked? So how many? So for one pair to talk, how many links are needed? Two links are needed. Okay. So how many switching paths should be available to ensure that no call is blocked? So one person calls here and here. So if A calls to B, two links will be used, right? Is it understood? If A calls to B, because this is A, this is B, suppose. So A will directly give it to switch and switch will give it to B. So to A and B, for A and B to communicate, how many links are needed now? Two links. Two links for one call. These two links. But if one this user gets busy, A and B get busy, so B and C cannot talk. So then C and D have to talk. So like that. So there will be like that A and B is one link. Like that C and D has to have another link. Like that, how many people can be at a call? There can be only 5 pairs at call because 11 customers are there. A is talking to B, C is talking to D, E is talking to F, G is talking to H, I is talking to J. So 5 pairs are there. So you will need 5 switching here. What they are saying is not, so you will need 5 into 10 links. But what is in this wording is that they are saying how many switching paths or lines should be available. So path is different, link is different. Link is this, A to switch. Path is A to switch to B. This is one path. So two links for one call or one path for one call. So this is where the trick is. Many people will say 10. Because one call takes two links. So you, as I have said, there can be as many as 5 calls. There cannot be more than 5 calls, right? Because there are 11 people. So if two of them are talking like that, pair. So if there are couples, so there can be 5 couples. One has to be not on call. Okay. So there can only be 5 couples. So 5 couples means 5 calls and each call takes 2 links. So there should be 10 links. But 10 is not an option because they are not asking for links. Here they are asking for paths. And path is two links make one path. So this is not a path because A is not talking to the switch, right? A is talking to another device. So this is not a path. This is just merely a link. So it may take many links to reach a path. So like that, if you have this kind of a situation where there, like this, there is a switch, a user is connected to a switch that is connected to another switch that is connected to a user. So how many links are needed for one call? 3. 3 links will be needed. These 3 links together make one path. So path is different, links is different. Here in this our scenario, 2 links make one path. So we need one path for one call. So we will need 5 paths because there will be 5 calls. So the correct answer is A. Is it understood? The difference between path and link? Okay. Next, with an encoding scheme of 12 bits per sample, what is the minimum required data rate to support the voice signal? Frequency range 3 to 4 kilohertz. So, if the voice signal's frequency range is 3 to 4 kilohertz, so we will take the maximum 4 kilohertz. So this is the bandwidth, we will take 4 kilohertz. Okay. Now, you people know Nyquist theorem? You know, right? Do you or do you not? No answer. Okay. So Nyquist theorem states that for a signal to be reconstructed at the receiver, it must it must be twice sampled at twice the bandwidth, sampled at 2 times bandwidth. So for voice signal, what should be the minimum sampling rate? The minimum sampling rate should be fs is equal to 2 into 4 or 8 kilosamples per second, 8 kilohertz. So if there are 8,000 samples in a second and then there are 12 bits per sample, what is the bit rate? You simply multiply these two. Bit rate is sampling rate into bits per sample. So there are 12 bits per sample and 8,000 samples or 8k samples per second. So this will be 8 kilobits per second. So 12 into 8 is, I suppose, 96 kbps. So the required data rate is 96 kbps. The correct option is A. Now we will be moving on to question number 6. Consider a TDM scheme with two customers. If in a time slot the probability that a sample arrives is 0.75 for each customer, what is the percentage of utilization in the TDM scheme? Okay, this one is a bit complicated. See, there is a TDM scheme with two customers. If in a time slot the probability that a sample arrives for each customer is 0.75, what is the percentage of utilization in the TDM scheme? Utilization means that when there is a particular time slot, if one of the, at least one of the, 1 minute, just let me get a sweater. So if one of the particular, in the particular slot, if one of the customers present a packet to be sent, then the time slot is utilized. If not, if none of the device customers are sending any packet, then the system is not getting utilized. So what this says is that there will be that if in a time slot the probability that a sample arrives is 0.75 for each of the customer, then what is the percentage of utilization in the TDM scheme? So in a particular time slot there can be 4 cases, right? There can be 4 cases. What are these 4 cases? That A's packet arrives, B's doesn't. A's packet arrives, B's packet arrives. A's packet does not arrive, B's packet arrives, and A and B, none of their packets arrive. So out of these 4 cases, which case will be considered as utilization and which not? Only the case where the both samples will arrive, that only in the case that both samples will arrive, since there is a TDM, so they can accommodate both customers. So only in the case that both customers arrive will there be, like, none of the customers arrive, both of the customers do not have packets to send, there will be no utilization. So the first case is that A's sample arrives but B's does not. So if A's sample arrives and B's does not, so what is the probability? That is, see, PA is 0.75, PB is 0.75. Now first case is A's arrive, B's does not arrive, so P AB bar, right? This will be, since A and B are independent, PAB bar will be simply PA into PB bar. So this will be 0.75 into 0.25. 0.75 into. So another case is P A bar B, where A's packet does not arrive but B's does. So this will be PA bar into PB. So this will be 0.25 into 0.75. Now, when one of their packets arrive, what is the actual utilization? Is the whole TDM getting utilized? No. When one of their packets arrive, only half of the packet is arrived. Half of the channel is getting used, right? There is TDM channel for both of them. So there are time slots for both of them. But only one of them is coming. So what happens is you will have only half utilization. But when both of them arrive, that is 0.75 into 0.75, then utilization is, here the utilization is 0.5. Why? Because there are two TDM slots and only one of the packets arrived. So utilization is half. Here also utilization is half because this is just the complement A bar B. In both cases, the utilization is only half because only one of the channels is getting used. But in PAB, both channels are getting used. So utilization is 1. Now, when both of the packets do not arrive, if no packets are arriving, then utilization is 0 because you are not utilizing anything. Your channel is just sitting idle. So utilization is 0. So we don't need to calculate the probability because anything into 0 is 0. So we just need to sum up these three terms multiplied by their utilizations. So total utilization will be, I'm writing here, so total utilization is equal to, so 0.75 into 2.25 into 0.5. This is one term. Another is just opposite, 0.25 into 0.75 into 0.5. And another term is another term is 0.25 into 0.25, sorry, 0.75 into 0.75, both of them arrive into 1. So total utilization will be, you do the sum, it will be 0.75 into 0.25. Can anyone calculate, please? What will be the answer? Let me calculate. Has anyone calculated this? Be active, man. So the final answer will be 0.75 or 75%. So only 75% of the time slots are used to transmit a message. So the correct answer is option C. Who is coming this late? Okay. So the option is option C. Now, question number 7. Suppose that there is a TDM scheme with only 2 available slots that can be allocated to any customer among all. Let there be 4 customers with individual arrival probability of 0.5 each. What is the probability of a customer getting blocked? So the TDM scheme has 2 slots and they can be allocated to any customer. There is no priority or preference. And there are 4 customers. So there are more customers than slots. So if 4 customers require time slots, then of course they will not get. So what will happen is 2 of them will get, Two of them will have to wait, or their calls will get denied. So if there are 4 customers, so if there are 2 slots and then there are 4 customers, so 4 customers cannot of course be accommodated in 2 slots, so each of them are arriving at a probability 0.5. So at a particular time there is a 50-50 chance that each customer will have a call request or not. So 0.5 probability they will have for call request. So what is the probability of a customer getting blocked? So when will this blocking occur? When, say, if the customers are A, B, C, D, if all of A, B, C, and D are not giving a call or not giving a request, then of course no one will get blocked. If one of them is giving a call, then also he will not get blocked. So all this P, A, B bar, C bar, D bar, A bar, B, C, D bar, these are all okay. These are all okay. Even 2, when there is A, B, C, D bar, means A, B, C bar, D bar, A bar, B, C, D bar, like this. These will all be okay. When does the issue arise? The issue arrives when there are more than 2 customers who are giving a call request. So it is 3 customers or 4 customers who are giving a call request. So A, B, C, D bar. What are the other probabilities? A, B, C bar, D, A, B bar, C, D, and A bar, B, C, D, and A, B, C, D. So in this case, all of A, B, and C are giving a call while D is not. In this case, A, B, and D are giving a call request, C is not. Like this one A, B is not giving, in this one A is not giving, and in this one all are giving. So okay, so all are giving. So this will be, what is the probability of this? Now the call requests for each customers are independent, so you can just multiply PA, PB, PC, PD bar, like that. Now like that you can expand all the terms. Now PA is equal to PB is equal to PC equal to PD. All are 0.5. All are 0.5. Yes, anyone raised hand? Anyone having any doubt? Okay. And if anyone is having any trouble understanding, please interrupt me. This is a problem solving session. Okay, this is not a class. So okay. So these are all PA, PB, PC, PD, they are all 0.5. And since it is 0.5, so of course PA bar, B bar, C bar, D bar, they are also all 0.5, right? PC bar, PD bar, these are all 0.5. So everything is 0.5. So you just give 0.5s. So this will have 4 0.5s, 0.5 to the power 4, right? This will also have 4 0.5s because ultimately all probability values are same, 0.5. So like that there will be 5.5 to the power 4 probabilities. So 0.5 to the power 4 means half to the power 4 or 1 by 16. So there are 5 such 1 by 16s. So the answer is 5 by 16. The answer is 5 over 16. And since 5 over 16 is not one of the options, the correct option is answer option D. This answer sheet will get uploaded, so you can check whether later. Now, why are buffers important? This is a theoretical question. Why are buffers important in scenarios? Okay, so the next question is, why are buffers important in scenarios where data transmission rates vary among connected devices? So to why are buffers important? So data transmission rates vary among connected devices. So the devices are not sending their data at a fixed rate. So if they are sending at different rates, some device which is sending data very fast, they will have all their data sent already when the other person has not even finished transmitting half of their data. So what will happen is, since like all of the data are not getting serviced together because the devices have differential rates, so there will be a queue build up. Okay, so since there will be a queue build up, since there is a queue build up, so some like this faster data, like if you want a uniform rate at the receiver, this faster device who is sending data very fast, you cannot send all of the data together because the other device is getting buffered. The other device is not that fast. The other device is slow. So he is sending 5 packets. By then another device has sent 10 packets. But you need 5 packets from this guy and 5 packets from this guy. So what will you do with the rest 5 packets of the faster device? You have to store them somewhere. You cannot delete them. So buffers temporarily store and manage data. So when devices talk at different rates, they can be synchronized. So even if you are talking very fast, only some of what you are sending will be sent to me in a particular time. Rest will be kept in a buffer and sent at a later time. So basically the buffer is slowing down the faster device so that all of them can have a consistent speed. And this is required, or else there will be no synchronization and you cannot communicate effectively. So this is to temporarily store and manage data. Question number 9. State true or false. Time division multiplexing does not essentially require buffer. So, time division multiplexing does not require buffer. Does it or does it not? Well, the thing is, time division multiplexing has particular slots. So, there are 5 slots, say. After 5 slots, it will return to the original user. So it will give user 1 slot, then user 2 another slot, user 3, user 4, user 5, then it will again go back to user 1. So in these 5 slots, until and unless all the 5 users have completed transmission, these 5 transmission channels will get blocked, these 5 transmission slots. So you cannot accommodate a 6th user. When there are 5 TDM slots, you cannot accommodate a 6th user, right? So since you cannot accommodate a 6th user, what you have to do is you have to store the data that the 6th user is sending to somewhere else. So TDM might need a buffer. But oftentimes TDM does not have a buffer. So what happens is, if there is a 6th user coming, well, too bad, his data will get lost. So TDM might require a buffer or might not require a buffer. So does not require a buffer is a strong statement. It's a false statement. It might or it might not. It's your design choice. But since the number of users is not in your hand, so if the number of time slots are less, you of course need a buffer, because losing the data that users are sending is not acceptable. Finally, a buffer is required in the case arrival rate is lower than service rate, arrival rate is equal to service rate, arrival rate is more than service rate. Okay, now you answer me this question. So you are standing in line for food, and the guy who is giving the food, okay, and people are coming and coming and coming. So if the guy is giving food very fast, he is giving food everyone fast, then will there be any queue? No. Even if more people come, he is very fast, so there will be no queue. People will take their food, leave, take their food, leave. But if the guy is giving the food very slowly, and people are coming in huge numbers, like during like this puja prasad, they give in prasad, so there is a huge line to get that prasad. So there are two rates at play here. One is arrival rate, how many people are coming to this rate is 0.2 packets per second. But say you are servicing, your packets are coming at 10 packets per second. Let's take an example. Packets are coming at 10 packets per second. Every 10 second, 10 new packets are coming, 10 packets per second. This is arrival rate. But each packet needs 5 seconds to service. So each time 10 packets are coming each second, but each packet needs 5 seconds to service. So will there be a queue or will there not be a queue? Come on. Tell me, will there be a queue or will there not be a queue?
Does it need queue, sir?
Yes, there will be a queue because each packet will need 5 seconds. So what is the service rate here? Service rate is 0.2 packets per second. So if arrival rate is greater than service rate, implies queue is formed. So if queue is formed, where do the data go? The data that has been sent, but they have not been serviced yet. Where those data go? They go to a buffer because they cannot be lost. So buffer is needed. So whenever there is a queue, you need a buffer to store the queue data because it has to go somewhere. So it will wait in the buffer, and once the packets before it will get service, then it will get service. So when arrival rate is more than service rate, a buffer will be required. So I hope this is clear. This is more like intuition and common sense. So I don't think this will be complicated. So this is what switching is all about. So that will be all for today. And for next day, we will go meet again Tuesday, 6 to 8. So do come at 6 o'clock and we will solve another assignment sheet based on week 2. So this was based on the week 1, and next session we will solve problems based on whatever is taught in week 2. So whatever is getting taught in the week wise NPTEL course, this problem solving session will be in sync with that. Okay. So that will be all. Thank you for joining. Have a nice day. You may leave the meeting. It must be sampled at twice the bandwidth, sampled at 2 times bandwidth. So for voice signal, what should be the minimum sampling rate? The minimum sampling rate should be fs is equal to 2 into 4 or 8 kilosamples per second, 8 kilohertz. So if there are 8,000 samples in a second and then there are 12 bits per sample, what is the bit rate? You simply multiply these two. Bit rate is sampling rate into bits per sample. So there are 12 bits per sample and 8,000 samples or 8K samples per second. So this will be 8 kilobits per second. So 12 into 8 is, I suppose, 96 kbps. So the required data rate is 96 kbps. The correct option is A. Now we will be moving on to question number 6. Consider a TDM scheme with two customers. If in a time slot the probability that a sample arrives is 0.75 for each customer, what is the percentage of utilization in the TDM scheme? Okay, this one is a bit complicated. See, there is a TDM scheme with two customers. If in a time slot the probability that a sample arrives for each customer is 0.75, what is the percentage of utilization in the TDM scheme? Utilization means that when there is a particular time slot, if one of the, at least one of the, 1 minute, just let me get a sweater. So if one of the particular, in the particular slot, if one of the customers present a packet to be sent, then the time slot is utilized. If not, if none of the device customers are sending any packet, then the system is not getting utilized. So what this says is that there will be that if in a time slot the probability that a sample arrives is 0.75 for each of the customer, then what is the percentage of utilization in the TDM scheme? So in a particular time slot there can be 4 cases, right? There can be 4 cases. What are these 4 cases? That A's packet arrives, B's doesn't. A's packet arrives, B's packet arrives. A's packet does not arrive, B's packet arrives, and A and B, none of their packets arrive. So out of these 4 cases, which case will be considered as utilization and which not? Only the case where the both samples will arrive, that only in the case that both samples will arrive, since there is a TDM, so they can accommodate both customers. So only in the case that both customers arrive will there be, like, none of the customers arrive, both of the customers do not have packets to send, there will be no utilization. So the first case is that A's sample arrives but B's does not. So if A's sample arrives and B's does not, so what is the probability? That is, see, PA is 0.75, PB is 0.75. Now first case is A's arrive, B's does not arrive, so P AB bar, right? This will be, since A and B are independent, PAB bar will be simply PA into PB bar. So this will be 0.75 into 0.25. Okay. So the next question is, why are buffers important in scenarios where data transmission rates vary among connected devices? So why are buffers important? So data transmission rates vary among connected devices. So the devices are not sending their data at a fixed rate. So if they are sending at different rates, some device which is sending data very fast, they will have all their data sent already when the other person has not even finished transmitting half of their data. So what will happen is, since like all of the data are not getting serviced together because the devices have differential rates, So there will be a queue build-up. Okay. So since there will be a queue build-up, since there is a queue build-up, so some like this faster data, like if you want a uniform rate at the receiver, this faster device who is sending data very fast, you cannot send all of the data together because the other device is getting buffered. The other device is not that fast. The other device is slow. So he is sending 5 packets. By then another device has sent 10 packets. But you need 5 packets from this guy and 5 packets from this guy. So what will you do with the rest 5 packets of the faster device? You have to store them somewhere. You cannot delete them. So buffers temporarily store and manage data. So when devices talk at different rates, they can be synchronized. So even if you are talking very fast, only some of what you are sending will be sent to me in a particular time. Rest will be kept in a buffer and sent at a later time. So basically the buffer is slowing down the faster device so that all of them can have a consistent speed. And this is required, or else there will be no synchronization and you cannot communicate effectively. So this is to temporarily store and manage data. Question number 9. State true or false. Time division multiplexing does not essentially require buffer. So time division multiplexing does not require buffer. Does it or does it not? Well, the thing is, time division multiplexing has particular slots. So there are 5 slots, say. After 5 slots, it will return to the original user. So it will give user 1 slot, then user 2 another slot, user 3, user 4, user 5, then it will again go back to user 1. So in these 5 slots, until and unless all the 5 users have completed transmission, these 5 transmission channels will get blocked, these 5 transmission slots. So you cannot accommodate a 6th user. When there are 5 TDM slots, you cannot accommodate a 6th user, right? So since you cannot accommodate a 6th user, what you have to do is you have to store the data that the 6th user is sending to somewhere else. So TDM might need a buffer, but oftentimes TDM does not have a buffer. So what happens is, if there is a 6th user coming, well, too bad, his data will get lost. So TDM might require a buffer or might not require a buffer. So does not require a buffer is a strong statement. It's a false statement. It might or it might not. It's your design choice. But since the number of users is not in your hand, so if the number of time slots are less, you of course need a buffer, because losing the data that users are sending is not acceptable. Finally, a buffer is required in the case arrival rate is lower than service rate, arrival rate is equal to service rate, arrival rate is more than service rate. Okay, now you answer me this question. So you are standing in line for food, and the guy who is giving the food, okay, and people are coming and coming and coming. So if the guy is giving food very fast, he is giving food everyone fast, then will there be any queue? No. Even if more people come, he is very fast, so there will be no queue. People will take their food, leave, take their food, leave. But if the guy is giving the food very slowly and people are coming in huge numbers, like during this puja prasad, they give in prasad, so there is a huge line to get that prasad. So there are 2 rates at play here. One is arrival rate, how many people are coming. To get this rate is 0.2 packets per second. But say you are servicing, your packets are coming at 10 packets per second. Let's take an example. Packets are coming at 10 packets per second. Every 10 second, 10 new packets are coming, 10 packets per second. This is arrival rate. But each packet needs 5 seconds to service. So each time 10 packets are coming each second, but each packet needs 5 seconds to service. So will there be a queue or will there not be a queue? Come on, tell me, will there be a queue or will there not be a queue?
Is it need queue, sir?
Yes, there will be a queue because each packet will get 5 seconds. So what is the service rate here? Service rate is 0.2 packets per second. So if arrival rate is greater than service rate, implies queue is formed. So if queue is formed, where do the data go? The data that has been sent, but they have not been serviced yet. Where those data go? They go to a buffer because they cannot be lost. So buffer is needed. So whenever there is a queue, you need a buffer to store the queue data because it has to go somewhere. So it will wait in the buffer, and once the packets before it will get service, then it will get service. So when arrival rate is more than service rate, a buffer will be required. So I hope this is clear. This is more like intuition and common sense. So I don't think this will be complicated. So this is what switching is all about. So that will be all for today. And for next day, we will go meet again Tuesday, 6 to 8. So do come at 6 o'clock and we will solve another assignment sheet based on week 2. So this was based on the week 1, and next session we will solve problems based on whatever is taught in week 2. So whatever is getting taught in the week wise NPTEL course, this problem solving session will be in sync with that. Okay. So that will be all. Thank you for joining. Have a nice day. You may leave the meeting.